this was yesterday's work. Basically what you want to do, Cameron, is you want to get the notes from somebody. There's not a lot, but there was a lot of explanation that went on to it. Okay, so this is charge, this is current. And we looked at current from the basis of two cells, a dry cell and a voltaic cell. When we look at a 9-volt battery, we talk about the voltage of it. That's what we're going to look at today. Okay? Now the key to this is remembering that electrons move from one space to another. Okay? That's what happens when we have an electric flow. And what do we need to have happen? We need a continuous loop in order for the electrons to keep flowing, right? We talked about that. What was the device that we used to measure the current? Ammeter. That's right. And it measured the amount of charge, didn't it? Okay, good. All right, so today we're going to look at what we call electric potential. Okay? First of all, potential. We need to write notes. No, I'm going to give you these notes. Except for certain things. Certain things I'll be a little more specific with. I'm sorry, I'm just going to get this set up better. There we go. Okay. So first of all, potential is basically the ability for something to happen. That's what potential is, right? You have the ability for something to happen. We talk about, as you get into grade 11 physics, we talk about potential energy. Sometimes we refer to it as gravitational potential energy. If I'm standing on the top of a diving board, I have the potential to create energy. Okay? Now, potential really refers to a lot of the time as more static or stationary, something that really isn't moving. Kinetic energy refers to something that's moving. In electricity, we refer to potential energy, electric potential as the difference between where an electron is and where it's going to end up, and the potential it has to create electricity or electron flow. So here it is. Whenever electric charges move through a conductor, work must be done on them. If work is done on the electric charge, there must be some energy applied. The energy applied to any circuit causing movement of an electric charge is called electric potential. So you need, in order to move an electron, you need energy to move it. You need to have work done on it. Well, what you'll find out in grade 11 physics is that work is energy. And we use that to solve a variety of questions. Work can be calculated by taking the force times the distance, the amount of force needed to move something over a given amount of distance. In electricity, the energy applied or the work done is called electric potential. All right? Potential energy is a common and welcome source of energy in many situations. We can describe potential energy as stored energy. And that's what I was saying earlier. When we talk about potential energy, we talk about it as being somewhat stationary. In this case, we talk about it as being stored energy. All right? The ability to maybe create electricity. Once the stored or potential energy is released, it is capable of doing work. Potential energy can exist in many forms. A stone on the edge of a cliff is an example of gravitational potential energy. So I just finished saying that. Me standing on a diving board. A stone at the top of a cliff. Those are what we refer to as gravitational potential energy. If the stone is released and falls downward, it will do work in a destructive way on anything it hits. Gasoline is an example of thermal potential energy. Gasoline burned in an engine can do large amounts of work. One of the easiest ways for us to understand the meaning of potential energy is to look at an example. A bricklayer was building a wall. He bent over, picked up a brick, and placed it on top of the wall. The brick now has some gravitational potential energy. The brick was accidentally knocked off the wall and fell down, landing on the bricklayer's toe. The potential energy of the brick has been changed into work done on the toe. to the bricklayer's discomfort. Okay? So if you're standing at the top of a cliff, if there's a ball, if there's a rock at the top of the cliff, we have gravitational potential energy. The moment we push it, it now starts to do work. Now the reason it's doing work is because it's moving and it's covering a certain amount of distance. Okay? When we talk about distance in terms of gravitational energy, we talk about height. The higher you are, the more potential energy you have for gravitational potential energy. Okay? What's the thing that affects anything and causes it to fall? Gravity. Gravity. The force of gravity. Okay? Now to find the force of gravity, we take the mass of the rock and we times it by the acceleration of gravity. And then we multiply it by the height. So the higher you are and the more mass you have, the larger potential you have to do work. Now think about that for a second. Got a 5-year-old kid, and I got somebody that's 6'5". Who has the potential to do more work? The 6'5" guy, the guy with more mass. Now, if it was the two of them jumping off a diving board from the same height, clearly he has more mass. He's going to make a bigger wave in that pool. Agreed?
He's probably going to get there fast.
Is he?
No, because it's the same type of gravity.
Yeah, it is. Now, yeah, but that's a good question. Does that affect it?
Like, say you do like a boulder and a rock downhill. I bet you the boulder.
What if they're the same mass? Okay, here's the old adage that they ask you. All right, which is gonna hit the ground first, a pound of feathers or a pound of rocks?
They're both pounds.
So they're not on the ground at the same time.
They're gonna hit the ground at the same time, aren't they? Because their masses are the same, right?
It depends on like how they're distributed too.
Well, this is what you're getting to.
Yeah.
So realistically, the little guy might hit the water faster because he's got less air resistance, right?
Yeah.
That makes sense?
Yeah.
Okay, because really the only thing that's holding you back, if you're moving at the same rate, which is called the acceleration of gravity, so each of you is moving at 9.8 meters per second every 1 second, because that's what it is. The guy that's going to have the less air resistance is going to go a little bit quicker. So the little guy's actually going to hit the water faster. But who's going to make the bigger wave? The guy with more mass. He's got the potential to do more work. Everybody understand that concept now? Okay, the potential to do work. So that works on gravitational. What we're trying to discover is, how do I create more work out of a battery? Or make more electricity, or make the electrons flow? And this is all about potential energy. The brick in our example demonstrates two characteristics of potential energy. This brick could have stayed on the wall for a long time. In this way, it represents stored energy. The brick could also have been moved off the wall at any time, whenever the work needed to be done. The ability to provide work on demand as needed is another characteristic of potential energy. So that's the other thing I was just mentioning. What we need to figure out when it comes to electricity is, how do we get that work done? How do we provide work on demand as needed? So that's what we're going to look at. All right. Now this isn't a very long section, but we're going to keep referring back to our two cells again, and then we'll talk first about electrostatics. So this charged electric force. Okay, again, the electric force is the plates, right? The aluminum plate on top of the foam plate, and then one was grounded and they transferred electricity. Remember that? Okay, so it's a good example of electric potential. When the neon bulb was brought near the electric force, nothing happened. But when the neon bulb touched the electric force, it briefly lit up as the electric charge ran through it. The electric force was able to store the electric charge, keep it separated from the ground, and it released it when it needed it to do the work. So push the electric charge through the light bulb. So we can call the stored electric charge an electric potential. So any electric charge For example, again, I go back to the same old because it makes sense to you, and that's when I'm walking across the floor in the library and I go to touch that knob, right? There is a static charge around it, around that knob. There's an electric force around that knob, right? Well, that one static charge has the potential to do electric work. So, and that's what it does when you ground it. When you come closer and you get to that knob and you get that shock, that static electricity had the potential to do that to you. It had electric potential. So any electrostatic, any electric charge has the potential to do work. Whether it's charge on the knob, whether it's the hair and the balloon, you have the potential to do electrostatics has the potential to do the work. Okay? So here's our voltaic cell again. Now an open circuit. When it's an open circuit, does the electrons flow through it? No? How come, Ellen? Because they're not connected. All right? This is sometimes a hard thing to comprehend. I always thought of that after. To me, if you open the circuit, that means that you've got flow. But it's actually not that. A closed circuit means that you create a closed circuit flow because your circuit is touching. An open circuit means that there is no connection here. So the electrons will not flow. Brock, you had a question?
Oh yeah, I was gonna say like it's kind of off topic, but like how what happens when you charge a battery? Like with a battery charger?
Yeah.
You know, like
So you're doing what?
like
You're putting an excess amount of electrons in. So you're doing it from a wall outlet, which you have an unlimited supply of electrons, right? Correct? And so, or somewhat of an unlimited supply of electrons. And you're putting it through the machine, and then it charges, and it puts the charge back into the battery. So you're putting more electrons into the battery.
But electrons are negative, are they not?
That's correct.
So you're like putting negative charges in.
You're putting negative charges into it. Remember, if you have an imbalance of them, then they can send them out,
Oh, I see.
right? Because right now your battery, if it's dead, it doesn't have enough electrons to circulate, to push it through. So you're adding those electrons into that.
So would there be like an equal amount of electrons and protons in the battery then?
Yes. Yeah. Okay, so direction of electron flow. We talked about that yesterday. Which way do electrons flow? Positive to negative or negative to positive? Positive to negative? That's what we figured out yesterday?
Yes.
You think so? And we want to clarify that to make sure?
Pretty sure.
Pretty sure.
Pretty sure.
I'd like absolutely sure.
100% sure.
You didn't even look.
Oh, I just know.
We don't want to get that wrong. Is it positive to negative or negative to positive?
I'm pretty sure of this down.
One of those things I told you had to write down.
What is this guy? This is negative 12.
Oh,
You should look, it's
Did
negative.
anybody find it? Look it up.
I have no idea where it would be.
Well, it's in here. It's in those sheets. Somebody find it.
Oh, it's in these ones.
Which way do the electrons flow? Do they flow from negative to positive or positive to negative? Where's all your sheets?
negative, positive.
They go
Yeah, they
negative
go
to
from
positive.
negative to positive. Yep, I was right.
Negative to positive. How come they go from negative to positive? We talked about it yesterday.
Electrons are the only ones that can move.
Because they're the only ones that can move. So what are they attracted to?
Positive.
So they're flowing from negative to positive, right? Okay, so you look at this, the direction of flow. We have the copper strip, which is the positive electrodes. The zinc strip is the negative electrodes, and then we have the acid solution inside the battery, right? In the open circuit above, the zinc strip causes electrons to build up at a point A and a deficiency of electrons at point B. This situation is very much like the electric potential on electric force in that there is a charge separation between the 2 points A and B. If a switch is inserted in the circuit above, we can cause the electric potential to do work by simply closing the switch and allowing electron flow or current to take place as the electrons flow from negative to positive. It was right there on the board and I just kept reading. For the record. Okay, An open circuit voltaic cell qualifies as a source of potential energy because the potential energy is stored for as long as the switch is open. The potential energy is on demand. The energy source, since we can choose to allow the potential energy to do work by closing the switch whenever we want. So it has electric potential. So you have a 9-volt battery, right? Everybody knows what the square battery looks like. And if you connect a wire to it, maybe a light bulb to it, it has the potential to do work as long as you close the circuit. Pretty straightforward, right? Go ahead, Brock.
You know what, like an EMP is? Like it's something-
EMP, yes I do.
Like what does that do to like shut down all electricity?
Okay, so it's an electro, I think it's not magnetic, I think it's, it might be magnetic,
It is
pulse.
magnetic, isn't it?
electromagnetic pulse. Okay, so it's, well, let's look it up. How about that? I better not give you some half an answer.
I don't know, I've seen it in movies where it just shuts down all the electricity and stuff.
Yep.
It's not like dangerous or anything, like it just shuts down electricity.
Electromagnetic pulse, which is considered a short burst of electromagnetic radiation. This kind of burst can come from a variety of sources, including our own sun. But in this case, we're talking about a pulse from a nuclear detonation that occurs at an extremely high altitude. When a nuclear explosion occurs in space above a target, 3 types of electromagnetic pulses follow. E1, E2, and E3. An E1 pulse involves high energy gamma rays colliding with air molecules nearly 20 miles above, then raining down electrons that go pulled in by the Earth's natural magnetic field. An E2 pulse comes from high energy neutrons that get fired in every direction. And an E3 pulse occurs due to the size of the nuclear fireball itself affecting the Earth's magnetic field. As nuclear physicist Dr. Yusuf Butt explained, these pulses affect everything in line of sight of the nuclear blast. For example, a blast at 60 miles can affect up to a 700-mile radius on Earth. However, there is a safe space that is unaffected by all 3 pulses almost directly below the blast thanks to the Earth's magnetic field. What can it do? EMP bombs do not cause casualties directly. The blast happens much too far away from people. Their power comes from interfering, disrupting, or damaging electronic equipment. That could mean power grids going down, cars and planes losing power, computer systems going berserk, and possibly even losing emergency backup power in facilities like hospitals. Sounds pretty scary. EMP blasts are a significant threat, but the effects largely untested and exaggerated through pop culture and inflammatory claims by politicians.
Mr. Newton, Ellen.
Go ahead, Al.
That's an EMP pulse solar flare.
We'll go to that in 1 second. Okay? So, basically, what is it? What are you reading from this?
Like it just shuts down all like
Yeah, how come?
it, I don't know, collides with Earth, like the Earth, air molecules.
Okay, so it collides with the air molecules, but what is it doing? What did it say it's doing? It's like
Excess amount of electrons.
what is it?
Excess amount
It's
of
an excessive amount of electrons, all right, overdoing everything electronically. And it gets pulled to the Earth's surface because of the magnetic field inside the Earth's core.
That's like crazy. It's like it like shut down like all like the people who were like living off there.
It would fry everything.
But if they were like living off like a defibrillator and stuff.
Yes?
Yeah.
Yeah, anything electronic, like so a pacemaker
Yeah.
on your heart. Sure. Any electronic equipment, because everything electronic is a flow of electrons. And so it overloads all of that, all of those electrons, it overloads it. And then that's what fries your system.
So if you set that off in like the middle of a big city,
It would paralyze your city. Right?
that would be-
But like they said, well, I don't think we need to go into the scary stuff on this, but it's not something that's happening.
That would look nice.
Probably when it goes on. It's just a,
That's probably just an
No.
exaggeration.
This,
it's like a radioactive.
so this, it's a better picture on there, it's not as easily seen here, but this actually says it's a peacekeeper missile defense system, is what that is. So, if, and basically what it does is it alters the electronics in the guidance system on a missile. Okay, is what it does. Alright? Okay, so now you wanna know what a solar flare is.
Is that when it starts? Well,
I thought it was when the sun, that's something the sun that goes back, isn't it? Yeah, it's something on the sun, yeah. And I think the way that's
What do you think it is?
it's something that has to do with the sun, isn't it? But it's something an explosion that comes out of the sun, but then turns back.
Sunspots.
Yeah. It's like a rainbow thing on the sun. Yeah, except less color. Yeah.
Alright.
Two colors.
So here it is. A solar flare is a tremendous explosion on the sun that happens when energy stored in twisted magnetic fields, usually above sunspots, is suddenly released. In a matter of just a few minutes, they heat material to many millions of degrees and produce a burst of radiation across the electromagnetic spectrum, including from radio waves to X-rays and gamma rays. Scientists classify solar flares according to their brightness in the X-ray wavelengths. There are three categories: X-class flares, which are big. They are major events that can trigger radio blackouts around the whole world and long-lasting radiation storms in the upper atmosphere. M-class are medium-sized. They generally cause brief radio blackouts that affect the Earth's polar regions. Minor radiation storms sometimes fall on M-flare. And C-flares are small with few noticeable consequences here on Earth.
Imagine if that would do to a person, like 20 degrees burns a person's skin.
Fried.
Not like you last very long.
No, not
Solar flares are different to coronal mass ejections, which were once thought to be initiated by solar flares. CMEs are huge bubbles of gas threaded with magnetic field lines. So all of this stuff that you're asking about has a lot to do with an excess amount of electrons, but it has to do with magnetic fields too. Okay, and everything that we have around the Earth, you have your magnetic field, your gravity. So you have an atmosphere around the Earth, right? In which there are electrons in the atmosphere around the Earth, but you also have inside the core of the Earth, you have a magnetic field from the movement of the fluid inside, and you'll study a little bit of that.
if that movement switch always happens.
Sorry again?
That movement switch. Like, isn't there something that your magnetic field can switch?
Yeah, if it actually, okay, so the long and short is this: is electrons spin, okay? They spin in a direction, and if you've got pairs of electrons, which you do in orbits, okay, if they spin in the same direction, they create a stronger magnetic field. If that spinning rotation switches, it can change what your magnetic field does. So if for instance, the magma in the core of the Earth, if it happened to switch directions, that would change your magnetic field drastically. Okay, so the Earth is spinning, correct? So is that fluid in the middle of the Earth, that liquid in the middle of the Earth is also spinning. And then you have electrons spinning on the outside of the Earth in the atmosphere. So all of it creates magnetic fields.
So
Okay?
if all of that changed, like would it change like what gravity does?
No, gravity's a pull, right? It still pulls you, but we don't need to worry about it changing. It's just not going to happen, right? But that's what happens when you have. So when we do electromagnetism in grade 11 physics, you'll find out that the poles, they all line up, but when your electrons spin in the same direction, your magnetism is greater in between them. So what we try and do is create. So I think we talked about this in this class even maybe. And in fact we did when we were talking about Rex's experiment. I was talking about an electromagnet. Okay, so you have a magnet. Looks something like this. And then around that magnet, we have coils of wires going around that magnet. Now, the poles themselves, what they call it, can't remember what they call it, but the electrons inside the actual magnet itself are spinning in a certain direction. By adding a current to it and creating more electron flow through it, you're now creating the strongest possible magnet you can have. And that's all because of the spinning of the electrons and the flow of it. So just by wrapping a simple wire, if you took a simple magnet and wrapped a wire around it and hooked it up to a battery, even a 9-volt battery, your intensity of that magnet would intensify an incredible amount. Okay, so you can create a much stronger magnet by just wrapping a wire around it and having the electrons flow through it. And that's because of the direction of the flow of the spinning of the electrons.
Didn't Brandon and Kozak do that?
Rex was the one that said he did it.
Brandon did something, kind of the same thing, he wrapped copper wire or something around the magnet.
Yeah.
And yeah, the spinning thing, I don't know, I just remember something of it.
Yeah. Are we doing, we should be talking about space sort of, but are we doing space in this season?
We hope to. We get to it. It might be the last thing we get to at the end, towards June. But yeah, that's the hope, anyways. Okay, let me finish this page off, and then I'll let you guys do some work here. An open circuit voltaic cell qualifies as a source of potential energy. Okay, we already talked about that. The potential energy created on an open circuit is called EMF. Now, this guy I need you to make a note of. Right here, please. The potential energy created on open circuit, on an open circuit, is called EMF, which is electromotive force. I want you to write that first line down that's in bold there, please. That's an important one. Potential energy created on an open circuit is called EMF, or electromotive force of the circuit. When we talk about the 9-volt battery, we say that the 9-volt represents the EMF of the battery, the total electromotive force, the total electric potential the battery has. So we use this term a lot when we do grade 12 physics. We do circuits. And we talk about EMF when we're solving questions. And that's the total amount of electric potential of all the batteries you have connected. Okay? So EMF is an outdated term because energy is not just force. EMF is retained even though the concept is incorrect because of its historical context. We've been talking about changing potential energy into work. Some examples illustrating electric potential energy changed into work. An electric saw converts electric energy into work done by cutting a board. Electric starter in a car, cranking a car engine. An elevator converts electric energy in moving people from one level to another in a building. This is a good time to look at a model of an electric circuit. A circuit consists of a device that has some potential energy, pathway for charges to travel, and generally something such as a light, oven, etc. that requires energy. In our analogy, we will have 4 strong people at one end of a tube that is filled with particles we'll call marbles. The young people are standing around waiting to go to work. They represent electric potential. On a signal, they begin pushing the marbles with a plunger. As soon as the marbles move 1 centimeter on their end, tube, the particles move 1 centimeter on the other end of the tube. Let me just see what they've got going on here. Okay, we're going to come back to that after. All right. So do we understand what electric potential is? Yep. The biggest thing is to understand what potential means. So it's the ability to create electricity. That's basically what potential means. Your ability to create electricity. Your ability to move electrons. Your ability to do work to move electrons and create electron flow. Does everybody understand that? So that's what electric potential is. Once the circuit is closed, we use the word voltage to tell us how much energy is needed to do the work of moving electrons through the circuit. If it takes 1 joule of energy to move 1 coulomb of charge through some distance on a conductor, we can say that 1 joule per coulomb or 1 volt of electric energy was needed. Let's look more closely at this description. Okay, so I'm going to use what they're doing here and I'm going to describe what's happening. First of all, when we measure energy, we measure them in joules. But we also measure work the same way. Work, energy, we will talk, or we'll use those interchangeably to describe what we're doing, and we measure them in joules. Right? I want to write this down. Okay? So work or energy is measured in joules. V represents voltage. Our unit of measurement for voltage is the volts. Now, electric potential, which is our voltage, is found by taking the amount of work required to move a charge a certain amount of distance. So what we will use, they use E over Q, which then means that I have joules per coulomb, which gives me volts. Now in grade 12 physics, we talk about voltage as work over charge, the amount of work required to move a charge a given distance. All right? And then what we do is we know that work is force times distance, so we use force times distance over the amount of charge, and so on. So they all kind of stem from this. So this is one of your very first formulas. This one and the one we did yesterday, I equals Q over T, that leads you into grade 12 physics. Okay? So E is equal to E over Q is equivalent to volts. The joule is a standard unit of energy in the metric system. Work is also measured in joules. Energy needed to do the work, in this case the work in moving electrons, is measured in joules. James Joule was a British scientist who had his own laboratory. Joule made many discoveries in physics that related to work and energy. It is in his honor that the unit of energy in the metric system is called a joule. 1 coulomb of electric charge is 6.25 times 10 to the 18. We already talked about that, right? The volt is a common term used to represent 1 joule of energy used to move every coulomb of electric charge. The volt is named for Alessandro Volta. So potential delivered. So here's what we wrote on the board yesterday when we did I equals Q over T, and I just did the same thing for you here now. Whenever work is done, there is a greater amount of potential energy before the work is done than there is after the work is done. That is, there has been a change in the potential energy. For example, the brick that fell on the worker's foot had a larger gravitational energy when it was on the top of the wall. As it fell, its potential energy decreased, but its ability to do work increased until it hit the worker's foot. The amount of potential energy lost in the fall would equal the amount of work done on the worker's foot. In electric circuits, the potential energy is the greatest at the negative strip, the electrode of the cell. Electrons do work as they move from negative electrode. As a result, the electric potential decreases until it's at its lowest value at the positive electrode. So it's gone around my circuit. In the voltaic diagram below shows an electric bulb connected. All right, so in the negatives start right here. That's the most electric potential you have. As you go through and you come through and you light up the light, you come back down, the least amount of electric potential you have is in the copper strip right there. This, as the electron current travels through the circuit, the electrons will travel from point A to point B. So quick little question right here. If an electric cell is to provide 1 coulomb of electric charge with 3 joules of potential energy to a device in the circuit, we can then calculate the voltage of the battery by taking 3 joules over 1 coulomb, which is 3 volts. All right? So, again, very simple, but very important to you if you take grade 12 physics. We spend 2 full units on doing electricity and studying how voltage and current, along with resistance, affects an electric circuit. The light bulb provides resistance because not all the electrons are going to flow through it because we have to light the bulb itself. Some of those electrons have to stay to do work to light the filament in that light bulb. Go ahead.
You know how you said like when you charge a battery, like you have to put electrons into it. How are the electrons distributed when the battery dies?
How are they? Okay, say that again. How are they
Like-
distributed
Yeah, like
as it dies, or
like
okay?
where do they go?
Where they go? They're lost
Just on with the
here, likely. Okay. Now think about this for a second, and I'm making this very, very simple for you. All right, but it's not necessarily how it happens. But what drains your battery in your car?
usually like cold.
Cold does, yes. Cold certainly does. Cold affects batteries because of the liquids in them. What's that? Leaves something on in the vehicle that drains the electricity. Okay? So if you leave your lights on, your car lights, and you come out a couple hours later, what's usually happen to your battery? It's dead. See, the battery will recharge itself, right? As long as the vehicle is running. But if you're drawing electrons from the battery, which you are to put your lights on, it drains all of those electrons out and they're lost. And then they don't come back in to the battery to recharge itself. Okay? So then the electrons are gone. So now you need to add an excess amount of electrons from your charger, put them back into the battery, and then you do it all again. Okay? Does that make sense?
Yeah.
All right? Okay. Any questions about that? You guys are, you are a long ways ahead when it comes to understanding grade 12 physics now. Because we do, like I said, all we have to do is add resistance to this, which we may do, I'm not sure, possibly do in the next section would be my guess. And we study the effects of resistance on electric circuits. So we add more batteries, we add more light bulbs, and we figure out how much resistance is lost, how much potential difference is dropped, or potential is dropped, and how much current flows through. Okay, that's all grade 12. And this is your very basis right here. This is where we started all right now. All right, remember what I said. You guys are getting the theory for everything that you're going to learn in grade 12. The only difference between now and grade 12 is we increase the difficulty of the math problems. That's basically what happens. You're going to learn all of this again. Got it?
And over in grade 10.
And hopefully you'll learn some of it in grade 10 as well. Okay, so what I want you to do right now then, please.
Do you teach grade 10 neuroscience?
Do I teach grade 10 science? I don't. Well, not yet. Who knows? I never taught this class either, so it's possible. Okay, so you had those questions from yesterday. You've got 20 minutes, 25 minutes today. You can work on them. I'm going to get you some electric potential questions as well. And other than that, you should be good to go. Rob,
Can we go to the partner, like, see if we got pretty much the same answers and stuff?
yes, you can work with a partner today as long as the volume stays down.
Can I use one?
Yeah. Let's not have a parade to the washroom today. Getting too much of that stuff. Okay, so if you need to check your answers, well, good. Who else is in here other than?